Hello, everyone. Welcome. How do I sound? Loud enough? Yes. Fantastic. This is kind of an intimidatingly large room here, but thank you, everyone, for coming out. I love the introduction. I guess I don't have to introduce myself. You all know who I am, so I'll just jump in here. We are going to be talking about how mathematics can really help us build better AI systems. And I want to start with a poll. I actually put this poll on the Wova app and got some amazing engagement on this. We got 27 people to answer it, maybe even more since I screenshotted it. But the question here for the audience was, how important is it to understand mathematics to build working AI systems? So I got 3 out of 27 telling me it's not important. I do disagree with you, those 3 here, but I will hopefully walk you all through why I feel like this is important and inspire you guys today and help you know exactly what areas of mathematics are important in AI design. We got 10 out of 27 nice to have, 14 out of 27 very extremely important. So jumping right in here, today we're going to be breaking through the hype. I know GenAI is absolutely the most exciting thing in AI these days. There's a lot of talk about Agentic AI, LLMs, generative AI models. And I think we're all so excited about these models because it really is a captivating model that's generating very beautiful results that sometimes we are maybe falling prey to the hype. These models are extremely powerful, but I think that they're not enough to bring working AI to the world today. And so I'm going to talk a little bit about how there's some specific mathematical models behind GenAI, what those models are, and then also give a little bit of visibility on the other mathematical models that we could be exploring to really bring this full circle and build some of the most powerful AI systems. So we're talking a little bit beyond LLMs today. Here's the agenda. I'm going to walk through very lightly the mathematics behind 2 core AI model architectures, first being neural networks, which is an LLM, and second is reinforcement learning, which is personally my absolute favorite algorithm. I'm also going to show an example project. I'm always tinkering with AI. I feel like it's the best way to learn these new concepts because there's so many new concepts in AI today. It's a little bit hard to keep up with. So personally, what I do is I'm just always building with it. And so I have an example project that actually really demonstrates how my knowledge of mathematics was able to guide an architecture decision in the software that prevents failures and leads to like visibility into what the system is doing. So I'm going to show that as an example. And then I'm going to wrap up with a little bit of my thoughts on what the next steps in AI might look like. All right, so here's the phases of the AI hype that I've seen so far. We started with big data. This is about when my career started. I graduated with my master's in statistics at the time when everyone was starting to talk about data science. So I came into the field working as a data scientist. I was using like linear regression, random forests, boosted trees, those kind of old school models that are still relevant today. And the large enterprise companies had so much data. We all knew data was one of the most important assets these companies had, but we didn't really know how to get value from it. So I saw this kind of wave that I feel was probably the beginning of AI, at least that I witnessed, where people are just trying to figure out how to get value and how to get predictions from large data sets. Then we moved into machine learning. This was kind of the MLOps phase. My career took a turn into like MLOps engineering. And that was where we were really doubling down on these predictive machine learning models. And we've kind of figured out how to harness our data, and we're starting to get value out of it. But we're setting up the right infrastructure to do that at scale. Next is GenAI. You are here. This is where we're at in the timeline. It is not the end of the timeline. It's probably the most exciting that I've witnessed so far through this timeline. But there's going to be something after this. And I don't quite know what that looks like, but I have some ideas I'm going to share with you guys. So very exciting to see where it goes from there. All right, let's jump into a project. So as I mentioned in my introduction, my hobby is I play poker. It's really just a way to apply my skills in mathematics. I love poker because it's actually really a lot of pure mathematics behind that game, and it's a very kind of concise, contained problem space for exercising those mathematics. So as someone who wants to tinker and build with AI all the time, I wanted to build an AI poker coach. And I actually have this thing up and running, but I'm going to show you how I used LLMs in certain areas of it and where I didn't use LLMs and the reasoning behind that. So what we're looking at here is, as a poker player, you want your chat component. You want to come out of a tournament or something and be able to talk to someone and tell them what happened. Oh, I had this hand, it didn't work out, this happened, I made this move, do you think I made a mistake? You want like this coach that you can learn with, and that's going to be a chat interface. So that's the LLM piece. You also have simple stats. I'll just go through and show all of these. There's simple stats like, how much did I make last year? Things like that. So you're calculating some very basic equations there off of just pure raw data that's accessible to us. That is not an LLM. So that piece is just some modular Python code that's completely separate from the LLM. However, I want the LLM, the coaching chat function there, to be able to reference those stats. So I kept that very separated in the code, but I allowed the chat component, which is the LLM, to retrieve that in like a RAG architecture. The third component is an advanced statistical model. This is predictive. This is a probability distribution that's really estimating how good of a player you are based on all your results over time. So this is a statistical model. It's probabilistic. It's much more advanced than those stats at the top here. But it is, again, a very separate module that I did not want the LLM to really even have access to. I wanted that completely separate, to be modeled in a more traditional mathematical way. And then again, I wanted the LLM to be able to interpret the results, but not try to calculate the equation itself. So you can see the equation there, although very beautiful, maybe not something that we want an LLM to try to parse. We really want the LLM to just talk to us, make us feel good, give us tips and tricks, know that information based on the data, but not calculate it itself. And I'll tell you the reason for that in a little bit. This is my somewhat ugly architecture diagram, but again, pointing out the modularity of this. So you have the mathematical module that is going to be your basic stats calculations, your basic analytics. You also have your more complex probabilistic model there. You have the data separated, that's tabular data. And then you also have a RAG system, and I'm sure many of you all are familiar with what the RAG is, but that's the retrieval augmented generation. So that's interfacing with the LLM. It's pulling data in from the math module, from the actual tabular data as well. It's going to inject that into the conversation. So it's really just providing the LLM context to have a very technical conversation with you. And it's really, I think of it as almost like the interface between the other mathematical modules here. Then you have your chat layer. This is what we're all probably building, very good at building. I use the OpenAI API, but there's a lot of APIs you can use for this. I used a reasoning model behind it. I think this is, might be O3 Mini right now, but you can toggle it. But that's actually the user interface there is how I think of it. It is an LLM, but I'm basically using the LLM here as a user interface between these other modules to help the human interpret and get value from the data that we're collecting. The last layer here is observability. This thing is not live. I hope to turn it on live and have like friends and family start using it. But when I do that, I want to know if it's going off the rails. I want to know if it's saying anything inaccurate. So I do have like logging and monitoring set up there. Awesome. So before I jump into how I use math to kind of guide that architecture, I wanted to just put this up here to illustrate what kind of math we need to know. I have my degree in mathematics, and I'm finding that in AI, I'm not using all of that degree. There was actually just a few core principles here that like kind of scoop up into everything AI. So starting with the foundational, it's linear algebra and calculus. These are actually not that difficult to learn. If you have basic high school math, it's kind of the next step there. If you have an engineering degree, you're probably already an expert in these. And these are actually just the foundational concepts that's going to be the language to learn everything behind the architecture of AI. And then above that is almost, I would look at it as almost an application of linear algebra and calculus. You have probability. This is actually one of, I think, the most important concepts in AI because these models are generating probabilistic output. And so having that kind of like intuition for how probability works has really helped me understand when and where to apply the LLMs. Optimization is a core concept. You're going to find it in software engineering, computer science, mathematics, probably physics as well. But that is over and over kind of the same type of algorithm I see implemented. And then that goes up to neural networks, and then that all kind of leads to what we really see as AI today. So I put this up here because I know mathematics can somewhat sound intimidating to folks who don't know it, but I just wanted to illustrate that it's not an entire degree, it's just a few core concepts. You're going to get them out of engineering, and it all kind of comes together to form AI. Okay, so question actually for the audience, and I know it's a big room, so just shout it out. I'm really curious how you guys define a model. What is a mathematical model? How would you define that? Just in human words. Anyone want to take a stab at it? Yes? A simplified representation of the real world. I absolutely love that. Anything else? A function. Yes, it is. Function of input and output. Awesome. I'm preaching to the choir here. So here's how I think about it. A model is a mathematical representation of a portion of our reality that encodes patterns from data and then leverages those patterns to predict future outcomes. I really like to think of the model as like a mathematical representation of a pattern we find in data, because that helps me kind of think like, okay, if I feed all this data into it, it's going to figure out in almost a different language how to represent those patterns that it found. And then when you come to the situation where you actually want to use those patterns to predict something new that hasn't happened yet, you have a great language for that. So that's how I like to kind of conceptualize it. I think that covers a lot of like machine learning models, neural networks today. There's two core type of AI models that I love, and they are both actually inspired by the human brain, which I find really interesting and maybe indicative of what could come next as well, because the two model types that are really just like a rocket ship in AI right now are actually just attempting, or at least inspired, to mimic us as humans and how we think. I'm not a neuroscience scientist, so I can't speak too much to this, but the architecture of neural networks is inspired by neurons in our brain. So it's basically like mimicking the brain's neurons by passing signals through layers that are like just mathematical equations there. And I'm going to show you exactly where the mathematical concepts come into this diagram. The diagram itself was generated by ChatGPT, which I think is actually why it's somewhat inaccurate, which is a great example here. But essentially what you're seeing is you have the data, which is an input layer, and then you have hidden layers, which are really just the mathematical representations of the patterns it's finding. And when you feed data into it, it's figuring out what those patterns are, encoding them mathematically, optimizing whatever you're telling it to optimize. You as a human have a lot of control over these systems, and it's giving you an output. So in the red here, you can see where these different math concepts come into play. We've got linear algebra, we've got optimization, and we've got probability. So those three concepts come into play here. This is what an LLM is. So what's wrong with large language models? They're super powerful. I use them all the time. I vibe code with them, actually. I use them to help me write emails and sound more human sometimes. So they actually become like quite helpful in our day-to-day life. There is something wrong with them, and what I mean by that is I don't think they're the end-all be-all for AI as we want to see it develop in the next like 5 to 10 years. They're not enough. I think they're just a piece of the puzzle. Here's why. Large language models are non-deterministic. So what that means is the output is probabilistic, and what that means is there's some variance in the output. So what that means here is if you ask an LLM my favorite color and you give it like a ton of data about me, it might get that right most of the time because it's making a probabilistic prediction. It's going to look at all the patterns of the data and decide what makes the most sense given all that context. That's essentially what it's doing. It's going to not always say the same thing. And where that becomes interesting from my perspective when I think about like where to apply LLMs and where not to, is essentially if you ask an LLM what is 1 + 1, it's going to say 2 most of the time. And that kind of variance is what it makes it sound so human and engaging in conversations, but it's also what makes it slightly inappropriate for like non-language based tasks when we need to be more exact. There are ways to tune this with like temperature and that kind of thing, but I think trying to use LLMs for everything and tuning parameters and fine-tuning the model itself to do everything might not be the right approach here. That's where my next favorite algorithm comes in. It's, again, based off of the human brain. In this sense, it is based off of dopamine and how our brains process dopamine. Reinforcement learning. So this is a bit of an old school algorithm. It's been around since I was in school. It essentially mirrors dopamine signaling in our brain by rewarding actions. The thing I love about reinforcement learning algorithms is they are so incredibly controllable because we are defining mathematically exactly what the reward is, what the actions are that it can take. And so when it goes off the rails, we can measure it very easily, whereas like LLMs, it's a little bit of a black box. It's a little bit more like you got to put evals on top of it. Monitoring is a little bit challenging. But the reinforcement learning gives the humans quite a bit of control, and you can also control the amount of randomness. You can allow it to go explore new patterns over here at just like a 2% rate or 10% rate, whatever you want, and then you can allow it to really optimize the patterns that are working very efficiently. So you're given quite a bit of control here. Reinforcement learning looks like this. It is essentially modeling an environment mathematically. And I think that's somewhat what is missing from LLMs today. I think LLMs are a beautiful kind of puzzle piece that do the conversational part of AI today very, very well. But I don't think that LLMs really have like a great view of what the environment is that it's interacting in. And so it's missing some data as it produces output for us. What reinforcement learning does is it allows you to essentially mathematically define an environment and then define the actions in that environment. And then you have what is called an agent, which I find very interesting because we're talking a lot about agents today, but this is a bit of an older concept of an agent. But you have an AI agent that's taking action in those environments. For me, this kind of brings things full circle, where if you start integrating LLMs into an environment or into an equation like this, not only do you have the power of language with that agent, but you also have the power to define and somewhat measure and somewhat control what that agent is doing. There has been a lot of work to like integrate reinforcement learning with LLMs. Reinforcement learning human feedback, the RLHF, is a really popular one, and I think that's a good kind of path towards integrating these two algorithms. So talking about like next steps in AI. So the way I feel this is going is when we look at like agent architecture. I love this diagram. It's not my diagram. It's from a different blog post that I can link. But this diagram is demonstrating very clearly how modular the design of agentic systems are today. And this indicates to me that there's this path forward here towards optimization that's going to start to look somewhat like reinforcement learning. It might not be exactly that, but I think it's going to start to kind of reflect those patterns. So what I'm seeing here is you see 4 different examples of agentic design patterns. This is going to basically be like a higher level software engineering diagram for a working agent system. You're going to see like multiple agents. Each agent is like an LLM that has specific tasks. So for example, when we look at the tool use pattern, there's 3 different tools that the AI can choose to use. And the user might come to the AI system and say like, hey, I'm trying to accomplish this specific goal. And then the AI reasons somewhat in a way, and then uses that information to choose which tool to use and then delivers the result to the customer. Or maybe it takes multiple paths through this diagram. But the reason this stands out to me is it looks kind of like this, because you have multiple actions. You have an agent trying to do these actions autonomously, which is what we're trying to get. It's more towards autonomous AI. And because it looks like this, we can now start to represent it mathematically, and now we can optimize it. Now we can start to, outside of the LLM, who's just communicating with the user and maybe deciding which path to take, we can start to optimize these different path choices, and we can start to measure and control that. So when I look at agentic design patterns, it starts to pop out to look more like an optimization problem to me with an LLM in there as a puzzle piece. And the reason I'm very excited about this is I hear there's a lot of research going on in this kind of agentic optimization area. We're optimizing prompts, we're optimizing routing decisions, things like that. And there's tools on the market, I'm lucky enough to work for one of them, that is starting to build this stuff out. It's how we do prompt optimization in an autonomous way. capturing feedback loop data from a human in the loop, and then using that to improve the system in a more autonomous way. So this is going to be somewhat of a software engineering and mathematical infrastructure that I think is going to become more and more of a popular pattern. To move towards the conclusion here, a little bit about the future of AI. So when I think about what's next for AI, I actually don't think about GenAI or LLMs. I think there's going to be something that looks a little bit more like reinforcement learning, and I think that these are going to be puzzle pieces within it. The areas of like new research that I'm seeing pop out that really excite me, that I want to just like spend all my time reading about, is a lot of stuff that's coming actually from Jan LeCun, and there's some other researchers in this area as well. But he's talking a lot about something called world models, which is getting us more to that mathematical representation of an environment where an AI can start to do more than just talk. It can make decisions, take actions, maybe connect it to robotics. So this is very, very exciting to me. It's letting LLMs just kind of be a piece of the puzzle. You're getting a more complete mathematical definition of the system. And maybe most importantly, to me, this starts to look safer, steerable, and more like something we can align ethically, because we're defining things like what is the goal of this thing. We're defining that mathematically. We can measure it. And we can toggle it on and off, and we can set temperatures, like how much randomness do we want, how much do we not want. And so you start to move away from like the black box model and move more towards something that is really somewhat more explainable, but still mathematical and powerful. I know that if anyone has a rebuttal to this, they'll say, but Clara, that's really expensive to run. It is, and so are LLMs, and I think that's probably another piece for us to figure out, is how to do this at scale. But these are the areas of research that I think are just really fascinating and will probably lead to the next phase of AI. So in conclusion, I recommend think like a mathematician, have that intuition of how these models work, and that will help guide us to build great AI applications, because we'll know which pieces should be LLMs, which pieces should be an if-then statement, which one should be a more advanced statistical model, and that just helps us piece together reliable systems that are not going to go off the rails. We've learned a few unpopular things today. First being study mathematics. It is helpful. When I first started majoring in mathematics, everyone was like, oh my God, I hate math. Like, why are you doing that? But it turns out it can actually be very useful in this age of AI. But you don't need all of it. Hallucinations are essentially, from my perspective, a feature of LLMs, not a bug. Yes, we have to measure for them. Yes, they hurt our business when it happens in a lot of contexts, but that's essentially how LLMs work, and it's also why they sound so human and relatable and powerful. It's just a nature of the non-deterministic algorithm. LLMs shouldn't do everything. I don't want to say they can't, because I actually see us like fine-tuning them and using them, and it like kind of sort of does it sometimes, and that's awesome. But I think as we experiment a lot with these things, we're going to figure out exactly what they should and shouldn't be doing, and we should use a different model. And yeah, the next gen of AI, I think it's going to look a lot more like reinforcement learning. I don't think it's going to be that exactly, and I think LLMs are still going to be in the mix, but I'm very excited to see what this looks like, and I'm following research on world models very closely. Cool, that is all I had. I want to open it up for questions. Yes? Oh, she's got the mic.
Are there any common mistakes or pitfalls that you see people hitting when they neglect or are ignorant of the mathematics involved with AI?
That's a very good question, and I can answer that easily because I have seen a lot. And I don't want to say it's like a mistake or a pitfall. It's actually just like what we should be doing right now is experiment. Like throw the LLM at a problem maybe that we don't even feel like it fits and like see what happens. We do need to figure that out. But the common mistake that I see people are getting better and better at not doing is having the LLM do your math instead of asking it to write code to do your math. Because code is a language, and I'm all about LLMs generating code, because I think the models actually capture patterns in code really well and are super appropriate for that. But if you have like tabular data or it's like JSON format and you want to like calculate an average or something, just ask it to write SQL, Python, anything to do that calculation and then run that over your data. But if you ask the LLM, hey, look at this data, like tell me what the average is, I don't like it. Good question. Anything else? Yes?
In the age where we see models rewriting algorithms and sometimes beating humans in that space, just in coding, right? Could a math amateur like myself use that same approach to not learn the maths and just have the AI do it for me?
Excellent question. I'll give my honest answer. I think no. But I think what you need to know has changed. You now need to know things at a much higher level. So like coding is a really good example. AI is actually really good at writing code, but it also makes some really dumb mistakes. And if I didn't have a background in code, I wouldn't notice that and be able to guide it. And so with AI, at least the way it is today, unless we improve the algorithms the way they're working today, I think to be a really good coder with AI and just delegate the AI coding, you need to know like high-level software design best practices, testing best practices. And you end up almost just kind of guiding the AI the way you would like a younger coder or an intern to almost kind of teach it those things and produce good quality code. If you don't do that, you end up with kind of a spaghetti mess that will break in production at this moment, unless these models get better.
Great, thank you.
Yeah, great question.
I just have a quick question about like what reinforcement learning would actually look like mechanically in AI. Do you think of it as kind of just like a loop of fine tuning as it goes, like tied in with like whatever evaluation metrics you're using?
Great question. Sure, I'd like to try that, but also no. I had a slide on that, but I didn't think I had time for it. So I don't like the fine tuning in that circle, actually. I like the LLM as like a chat interface, but in some situations, like fine tuning the model makes it really good and gives it like the right context on a very specific problem. In other situations, the fine tuning, instead of fine tuning, it should maybe be a different algorithm, and maybe we're fine tuning it because it's not working because it should be a different algorithm. So I think we're gonna kind of see both patterns there.
Cool, thank you.
You mentioned adjusting exploration rate.
Yep.
Could you talk about how do you determine the randomness in the applied system, and what happens if you got it wrong?
Yeah, great question. That is what I was touching on, is defining the explore exploit, because there's this toggle in reinforcement learning where you can tell it how much to exploit a pattern that's working versus go explore and find a new one. So very much the way like humans learn. In terms of actually tuning that, I think that's a whole art and science, and actually depends somewhat on the business problem and how comfortable we are with the explore exploit. So for example, with my app that I built, it might be a situation where I really don't want it to throw any randomness in, because then my users might lose trust. So there's things like that where you maybe want to test it offline and pre-train it. But it really just depends on the use case and what the impact is of the exploration. Yeah, sorry, I don't have a better answer to that one.
Yeah, I was just going to ask, what's your take on small language models versus large language models, and what's also your take on basically, I guess, the landscape of just like autonomy versus actual, like a prompt injection type of security vulnerability that can potentially be
Yeah, so the question was twofold. It was large versus small language models. I'm not an expert in small language models, so I actually don't want to touch too much on that one. But I do say like it is attractive to me because it's modular. You just have a little guy over here doing one thing, and then like if one thing breaks, you know who broke, you can go fix it. So it seems a little bit more testable. And then the other question was around like autonomy versus security vulnerability. Personally, I love human-in-the-loop AI these days. I want to move towards more autonomous, and there's some areas where we can, but we're not replacing humans. I think we're trying to augment humans and take away the grunt work or the work we don't want to do and make us more efficient. And I think there's just a lot of places, especially with AI being so new, where I want a human in that loop interacting with that AI, and that's typically the best designs I see today. Yeah, thank you, everybody.